All right.
Which one do you think that's the one?
Oh, yeah. Which one is it? No, it's not that one. All right, so watch. So here's the formula we know for confidence intervals. And just to remind you guys, this comes from this formula that we knew from before, right? So if I don't know the mu, what do I use? X bar. And then I want to go, this is all about going so many standard deviations away from the mean. So if I take a sample, the standard deviation's got to change. And then why is it plus or minus? Because I want to go up and down. I want to catch the middle whatever percent. So that I'm that sure that I caught a specific data point. So the idea behind this is actually one of the easier ideas to get, because there's a lot of visuals. I got the whole fish net thing, right? You're throwing out the net to catch the fish, even though I would never do that because I hate fishing. So where do we leave? Oh yeah. So what's this part here? What did I call that part? Error, yes. So I'm going to say the error is this. That's the error, right? Is that cool? So if I know the sample size and the z-score from how confident I want to be and the standard deviation, then I can figure out what the error is. And that's where we start. We do the error first. So here's the interesting thing. What if I know how close I want to be, but I don't know how large of a sample it would take to do that? So let's say I wanted to be within 1 mile of a guess of where something is on the moon or something. Right? So I know how close. So that word within is a key word for error. Within so much is how off you are. So it's the error. Are you guys kind of with me so far? So I know how far off I want to be. I just don't know how large of a sample I got to do. So it's sort of a feasibility study. So if your boss came and said, Johnson, I want you to be within 3 of this. And you're like, well, boss, it would take 8 million people in our sample. Oh, shit. That's not feasible. Maybe I can scale that error back. Maybe I can be okay with more error. So if they tell me what the error is, and I want to know how big of a sample I have to take, I need to solve this for n. Here comes the little bit of algebra that we use. How do I solve that equation for n? Just like we did to get this equation, what did we do? We took this equation and we solved for x, right? So here I want to take this equation and solve for n. How do I do that? Okay, good. So I've got a couple of things going on. What I would do is multiply root n up, and then you'd also divide e down. So the one cool thing about algebra to get is you can just switch these damn things. Right? Because what is 10 divided by 2? 5. And what is 10 divided by 5? 2. Those just switch. Why? Because they do. Because that's how numbers work. So I can just switch these. Bam! Square root of n equals z sigma over e. Right, that's multiplying that, dividing that. That accomplishes that. But bam. And then how do I get rid of the square root? Square. So the formula, this is the formula that's on that handout. The formula for sample size required is this. So that's right there. I just distributed the square there. Is that cool? Either way you want to do it. All right. So on this problem, let's see what it says. How many women would you need to sample to be within 0.5 inches of the true mean height at 98% confidence? So this one, we already know what was the z-score we found out for 98%. 2.33. And it's still the same problem, so I know the standard deviation is still 64.17. Right? Yeah. And what's my error that I want? How far off do I want to be? What's the error in the height that I want?
No, the standard deviation is 2.5.
What did I do? Oh, that's the height. Standard deviation is 2.5. Thank you. I left out most of you guys just weren't along with it. Sure. That was the average. All right. So my z-score is 2.33 for that confidence. Standard deviation is 2.5. That makes more sense. How far off do I want to be? 0.5. And it's not always going to use the word within, but that makes sense. That's kind of a key word, is how far off within. You want to be within this much. So now, like always happens in most fields that use math, and stats is one of those, it takes a while to figure out the idea and then to do the algebra of solving the equation, but then it's just plug and chug, right? You guys probably want to see that. So now I just plug and chug. What's the z-score? 2.33. Standard deviation? 2.5. To be honest, it's better probably to do this. You can do it either way you want to. So 2.33 times 2.5 divided by 0.5. And then all that squared. Or you could do this way, whichever way is easier for you. It's 127. What is it? 135. 135? Be very precise. 135.6 or 7? It actually doesn't matter. 135 point, who cares? I know. You're like, be precise and then, because what does this represent? What does that represent? What does that represent? How many women? Can you have 135 point, who cares? Women. No. So I really want to make sense. To have the air get down to 1/2 inch, I need to have at least 135 point, who cares, women. So what should I do with that number? Round it up. I want to be more precise. If I round it down, then I'm not going to be within 0.5 inches. I'm going to be within 0.502 inches or something. So you always round this number up. So I need 136 women. How are we feeling so far? Okay, cool. Now real quick, what was the sample size up here? 34. And what was the error we got up here? Because I don't know what I do with my work. Do it again. So, 0.999? So we got within like 1 inch. I really want you guys with me. So when I take a sample of 34, I get within 1 inch. On part B, I wanted to be within 1/2 inch. Does it make sense that takes more people? Of course it does. If you want to be closer to the right, you better take a larger sample. I like it. So what we got makes sense. Sometimes I'll ask this question like, how many more women would I need? Well, how many women do I already have in my sample? 34. And I need how many total? So if I say how many more women, you would say 102. You need 102 more women to get your error down to 1/2 inch. Okay, maybe. So when the question says, how large of a sample would you need, or how many would you need to be within, or something like that, that's the n equals equation. You want to solve for how large of a sample, or how many do you need. Okay, maybe. Okay. So any questions about, I know I don't have the work we did last time, but any questions from this handout before we get into the next level of stuff? Okay, cool. Hopefully that's a good sign. Okay. So like I said earlier, and I think I said this before, I'm skipping A2 for just a minute. We're going to do 8.3 next, and then we're going to come back and do 8.2. Because 8.2 introduces kind of a new distribution. Right? You guys are like, what? 8.3 uses the good old normal distribution. Okay. So here's what's cool about how to get this equation that I need. So tell me, how did I develop this equation? I started with this equation, right? Is that cool? Okay. What kind of situation would I be in? What kind of situation have you seen where I talked about percentages? And I was talking about probabilities that there was, the percentage was something or other. How do I say this? Like, for example, 11% of people like lima beans. You take a sample of 80 people. What kind of problem is that going to be? Can somebody help me? Take a sample of 80 people. What's 80? What's the symbol for 80? Take a sample of 80 people. N. 11% of people like lima beans. What's that going to be? Holy shit. Okay, so we're talking about NPQ problem, right?
Yeah.
All right, cool. I like it. So I'm going to do this. I'm going to start to construct the formula that I need. I'm going to start with this again. All right, stay with it. So this gets interesting. And a couple of side notes. What is the difference between these two symbols? The difference between these two symbols.
One is the mean of the population, the other is the mean of the sample.
Exactly. So the population, we wanted to be all official and formal, so we make it Greek letters. Right? And the sample, we just make it our letters. Like, yeah, you just a sample. How are we doing so far? So when I write this, that is the percentage of the population. So when I say 11% of Americans are left-handed, that is a statement about a population. Is that cool? If I said I take 12 of you and I find that 9% of them are left-handed, that is a percentage of a sample. So hopefully it makes sense that I want to represent that with this different symbol. The same reason I want to differentiate between these. So you're going to love this symbol. P is the population percentage of success. Is that cool? So then Q would be the population percentage of failure, right? So I'm not even going to write Q up there. It's there. The get out of there, Jeff. The percentage of success for a sample is P hat, right? P hat. Something you don't want to wear more than likely is the P hat. No, okay. If you've ever gone fishing, all right. So P hat, that's what we call this. That just means exactly, it's sort of like X bar. It's X with that thing on its head. It means the sample mean. So P with a hat on its head is the sample percentage. So now help me out. What we need to do is take these and use the formulas that come from the NPQ kind of stuff. So help me out. What's the formula for the mean?
N times P.
Yeah, so for this it's N times P. So what do you think the formula is for X bar? Let's see if somebody can get this.
N times P hat.
That's crazy, right? For X bar is a sample mean, so it's probably N times the sample percentage. It's crazy. So, NP hat. So this, just like I had to replace it with X bar, I'm going to replace this with NP hat. Maybe. Okay? By the way, just to remind you guys, because I want to make sure everybody understands what's happening. I'm deriving a formula right now. You're never going to have to do any of this yourself. You are constructing a formula. You're going to use the end result. So if anybody's out there like, I can never do this shit, it's fine. You don't have to. Then here's Z. We'll do plus or minus just like we did here. And what's the formula for the standard deviation? Good. Square root of NPQ. So what am I going to probably use? Square root of N, P hat, Q hat. That's crazy. So this will be square root of N, P hat, Q hat. I love it. So what did I do? Just like I did here, what did I do? I replaced mu with what I got from a sample. I replaced sigma with the new standard deviation, right? So now I want to take mu and replace it with the mean for a sample that I know the percentage of. And I take the sigma and I replace it with the standard deviation formula. Right? So it's kind of nice I'm starting with the same equation, because what I still want to start at the middle and go up and down so many standard deviations. So I still want to use this formula. I just have to put the stuff in that makes sense for the distribution I'm using.
What does the Q represent in this case?
Yeah, what is Q? If P is success,
Oh, failure.
Q is the percentage of failure. So there's a Q here and there's a Q hat, right? So what's P hat plus Q hat?
100.
100% or 1. So I don't care what they're wearing, P and Q have to add to be 1. P sock and Q sock is 1. There is no P sock and Q sock, by the way. That sounds horrible. Okay. You guys, let's just do the math, boy. All right. So what does this capture? What's the whole idea? Why did we do this? What are we trying to catch when we do this? Fish. I love it. But what do we say? What's the thing we say? We are 95% confident that this interval I just made contains the true, okay, we're trying to catch the true mean. And when I say true mean, I mean the mean of the whole population. I love it. So this, I'm trying to capture the mu with this, right? All right. So this next step is a little less rigorous. I don't care because it's basically right. Now if x bar is np hat, mu is np. I love it. Yeah, I can't even imagine what you're thinking right now, but stay with me. I mean, do you guys understand? Is everybody cool with that formula there? Yes, you have to be, because that's the formula we use. So I'm just replacing, what have I done so far? I replaced that with the sample stuff for NPQ problems. I replaced that with the standard deviation for NPQ problems. I haven't done much yet, to be honest. Maybe that's why you're leaving it. Come on. You haven't done anything. Okay. And then that's what I'm trying to capture. But is this a standard deviation? Is this a confidence interval of percentages? No, this is still a mean here. So I want to get rid of the freaking n. I want it to be a percentage, give or take some percentage. I want to say 44% give or take some percentage. That's what I want. And this n is in my way. So what I do then is I freaking divide by n. That's insane. So if I divide by n, I'm going to capture p now, right? So if I divide by n everywhere, all right, let me put this up here. We're almost there. We're almost there. I can see all the way over there. There we go. So where are we at? We got to capture the population percentage. I start at the sample percentage, and I go up and down so much. Now I can do a little something here. Let's see if you guys remember. Can I divide these? Can I kill those n's?
Yeah.
No, because they don't have the same radical, right? Remember that? You can only divide square roots and cube roots. They have to have the same radical. Do you remember that? Square root of 2 times square root of 7 is square root of 14 because they have the same root. Oh shit, algebra is actually important in the real world. No way. Alright, maybe. So what I can do is n, isn't n the square root of n squared? Do they have the same root now? So then I can reduce the n's. How many n's would be left?
One.
Where?
Bottom.
Beautiful. So now I got this. That's what we end up. That's the formula. Get out. Not that. That's the formula for the confidence interval for a percentage. I know I'm a little insane because I probably show you more than some other math teachers might. But it's good to know where things came from. I built this formula, and the same way I built that formula, I have to be able to because they're basically the same idea. Just one is about means and the other is about percentages. So let's do this. Let's do a concrete example of this. That's always nice. Come out of my algebra. Let's do a concrete example. All right. Has everybody got what they want from this?
Yeah.
Yes.
Instead of square rooting the bottom, could you just square the top?
No. I didn't square root the bottom. I really want you to understand. N is the square root of n squared, especially because n can't be negative, so I don't have to do absolute value. What's the square root of n squared? N. So wherever I see n, I can replace it with square root of n squared all day long. So I didn't do something to the bottom, I rewrote the bottom. I know, and that sounds like you're like, oh, you math could be a little tricky stuff. No, I can wherever I see 5 plus 3 in the universe, I can replace it with 8. Did I do something to it? No, I replaced it with something that 5 plus 3 means. So I replaced n with what it means, square root of n squared, which made it possible for me to reduce that to just a single n on the bottom. Maybe. Yes, sir.
Isn't it still an n squared?
No, because this n canceled with one of those n's. So now it's just the one n left alive. Okay. When I do math, I always have like zombie apocalypse. Who's left alive? Where are the survivors? Okay, all right. All right, so here we go. What would a problem look like now, dear God, Jeff? Well, now that we have that formula, that's really all we need. So let me write it again here a little prettier. So let's say we talk to 412 people, and 198 of them say they like, sure, lima beans, why not? Stick with the lima beans. Find the 90, let's say the 90% confidence interval. For the true percentage of people who like lima beans. What I love about this problem is it doesn't feel like it told me a lot. Do you guys see that? Does that? I don't know if you feel the same way. This doesn't seem like it told me as much as the other problems do. Tell me one thing, and then they ask me a question. I'm like, holy shit! But I gave you everything you need to know. Let me see if you guys remember this. Why would a problem not have to tell me if it was normal or not? We've seen some of that in the book. If what's true, what makes it normal enough?
If we have a standard deviation and the sample size is over 30.
Good, okay, there you go. If your sample size is over 30, the picture of the sample means will be normal enough, right? And we had the whole discussion earlier about what that really means. So when you graph the means, that becomes normal enough. I like it, cool. So for this situation, who remembers, we talked about this briefly, it was on that practice test, and I ended up not putting it on the actual test. But what's the check for NPQ? Greater than 5. So the first thing I want to check, actually the first thing we got to make is what the hell is p hat? What is p hat? And just look at the problem. Can somebody tell me the percentage related to this problem? What's the percentage? Yeah, 198 divided by 412. That's the percentage of people who like lima beans. And liking lima beans for this problem is a success, right? Or maybe you guys get that. So don't make too much out of that. The percentage is just staring you in the face. You got to know how to make a percentage. They're going to tell you the total, will tell you the people. So what is 198 divided by 412? Rounded to 3 places, at least. 481. So what's Q hat? 0.519. I like it. This is 1 minus that. You whatever the P is, you 1 minus it to get the Q. I like it. So before I can look up a z-score for 90%, I have to know that it's legal for me to use the z-score chart. And when is it legal for me to use that chart? When I have a normal distribution. And how do I check it? In this case, NP and NQ. Right? In other words, NP hat, NQ hat. Let me see if somebody gets this. If you don't get this, you can just multiply them and go to town. How did we get p hat? What did we do? We took 198 divided by n. So what's n times p hat? It's going to be frickin' 198. If you get that, it's so much quicker. The number they give you is the n, is the np hat, correct? If you guys see what I'm saying. If you don't see what I'm saying, take 412, multiply that by 0.481. What do you get? Roughly 198, right, if you don't believe me. So you can always do that work. You can always do that. Some of you guys hopefully will realize the number they gave you is the freaking NP hat. That's how I made p hat and divided that number by n. So what's n times p hat? It's going to be that. Shit. So then what's NQ hat? It's going to be the rest of the people. How many other people are there? 214. Yep. And again, if you don't believe me, you can do 412 times 0.519, and you'll come out with roughly 214. Right? Did anybody do that? Or do y'all just trust me? It's less work to trust you, so screw it. And these are both what? greater than 5. Which means that this is normal enough. Which means you can do something, yes?
How'd you get 0.519 again?
Whatever P is, I don't care what it's wearing, you get Q by doing 1 minus that.
Okay.
Yeah, always. They have to add to be 1. Kick ass. All right, so have we even started making the confidence interval yet? No, we haven't. All right. So how do I make the confidence interval? Well, I need P hat. We know P hat. So 0.481, give or take. Now, what's the z-score for a 90%? Is that in your little baby chart? 90% confidence interval, what's the z-score for that? 1.645, cool. So then I got 1.645 times the square root of 0.481 times 0.519 divided by 412. The biggest mistake I see is people think this is n. That's just a part of this. That's n. N is everybody you're talking about. When A is part of the people you're talking about. So let me show you how to put this in the calculator, because that's the next thing we have trouble with. Stop. Show me. All right. Let's see. Boop. So it's what do I start with here? Oh, yes, sir.
What's the number you have there next to the check mark? Under the 198 greater than 5?
And then 214 bigger than 5.
Oh, okay.
And Q hat is 214, and that's bigger than 5.
Oh, okay.
So they're both bigger than 5, so it's normal enough. What part of this do I do first?
Error?
The error. Beautiful. So do this part first. So do 1.645 times the square root. Now this is an older version. If you have the one where the square root bar just grows, you're golden. Just that whole damn thing has got to be in the square root. Do you understand? So some of you guys know what I mean. You have newer calculators where the square root bar just grows, so you know exactly what it covers. If you have an older one like I do on the computer anyway, just don't close the parenthesis until you get all the shit in there. The minute you close it, you're outside of the square root now. So what I mean by that is you put, where do you go? 0.481 times 0.519 divided by 412. See, I haven't closed the parenthesis yet. Now I did. Now I've got everything in the square root that I need in the square root. So everybody should get that. I like it. All right, so let me... Oh, you just missed all that. Sorry. All right. Let me see. So let's see. We don't need this here anymore. Or this. So let me put this up here. So what do we got? We got 0.481. Give or take 0.0405. I like it. And now it's just the same. It's a confidence interval. It should have the same structure of work that any confidence interval does. I'm going to add that to that, subtract it from that. That's going to be my interval. And then your conclusion is the same. We are 90% confident. So what do we get here for the interval?
4405.
What is it? 0.441. Yeah, there it is. And then 0.52. 522? 5215, I like it. Cool. That's fine.
So it doesn't matter how many standard deviation or...
So in general, it's always one more decimal place than what's here.
Oh, okay.
In general. I like it. And then, after that, you could round these a little bit if you want to. The important thing I really want you to understand is you don't round much before you get to the end of a problem. The more you round early, the more off your answer is. That's really the key lesson between all this stuff I'm trying to get you to do with how much to round it to. So what can we say? We are 90% confident that what?
The interval...
The interval?
441 to
44.1% to 52.15%. Yeah, there you just make it a percentage so it's more human, right?
Contains the true mean.
Percentage.
Percentage, good. Everything's about percentages. That the interval that contains the true percentage of people of lima bean likers. Not lima bean lickers, I don't know. So it's got very similar structure to it. The formula is different because formula for standard deviation, I need one for in the first place. If I give you a mean problem, I'm going to have to tell you the standard deviation. Here, we make our own standard deviation. That's what that part of the formula does. And that's why that's different here, because I didn't have to do that before. They should give it to me. Maybe. Maybe. So if somebody thought that 52% of people like lima beans, what would this study say about that? They thought 52% of people like lima beans. Does this study say that that's wrong? No, because this could be 52% very easily. So this wouldn't say it's wrong. It doesn't prove that it's 52. It just says I can't say that's wrong. You guys would. So if I was really weird and I was really like